Hi, gang. Dave Hicks here, and today we're going to talk about the Index of Hydrogen Deficiency. So, this is part of a package of things that I'm going to be showing you on analyzing hydrocarbons. And, in chemistry, we've already seen that we can do chemical analysis that will give us some things such as the empirical formulas and even the molecular formula if we can come up with a molar mass for a substance. So we can come up with those types of formulas like CO2 or C3H8. But how do we know what the structure looks like? In chemistry, carbons can bond together in so many different ways. We need to come up with some tools that will help us to understand which is the way that this particular molecule is put together. So one of those tools that I'm going to teach you about today is called the Index of Hydrogen Deficiency. So what does the Index of Hydrogen Deficiency do? It measures what we call a degree of unsaturation. And the degree of unsaturation comes in two different forms. It can either come in the form of a pi bond. Whoops, excuse me there. It can either come in the form of a pi bond. There we go, I got my pen. Or, I thought I had my pen. I want the pen. There we go. That's not the color that I want. Let me see if I can get the pen color that I want here. Sorry about the delay. And we'll go back to my slide. There we go. So the degree of hydrogen deficiency is focused upon either pi bonds or it's focused upon the rings that could be formed in our molecule. So we can either determine this from a chemical formula, and again, this would be like CO2 or C3H8, or we can look at the structure itself of the molecule. Now, I don't find it too helpful to look at the structure itself and talk about degrees of hydrogen deficiency because the structure is what we're trying to get to, yes? So usually this gets used in a way like we take a formula and figure out from the formula what the structure is going to be. So generally we do this degree of hydrogen deficiency or the index of it, and we do that with the chemical formula. So it measures unsaturation. Somebody has sat down and come up with an algorithm for us right here that can tell us what a saturated hydrocarbon is. And so it says, hey, if I have n carbons and 2n plus 2 hydrogens, then that would be a saturated hydrocarbon, right? So let's test that theory a little bit. So what if I have CH4? And CH4 here would be 1 carbon, so here N is 1, and then it would be 4 hydrogens, so 2 times 1, see the same N, those two N's are the same, 2 times 1 plus 2, that would be 4. So you can see that is the formula for methane, which is a saturated hydrocarbon. Let's choose something a little bigger, huh? How about C2H6? So if the carbons were 2, there's 2 carbons in it. See right there, the 2? 2 carbons, so 2 times 2 plus 2 is 6. There's ethane. We know ethane is a saturated molecule. Let's try one a little bigger, shall we? How about octane? C8H. C8H18. There we go. So if I've got 8 carbons, and 2 times 8 would be 16, plus 2 more, 18 hydrocarbons. Or how about if we could go from a name? How about hexane? Can you do it? Can you write the formula for it? Should you give it a try? I'll give you a couple seconds. All right, hopefully you know that hex means 6, so there's 6 carbons. And then the hydrogens would be 6 times 2 is 12 plus 2 more, 14 hydrogens, huh? So there we go. This is a saturated hydrocarbon. Well, you can kind of see that in our degree of hydrogen deficiency up here. So let me zip to the next slide and show you how to use this formula. So in the formula here, this is 0.5, or what I do in the end is I just divide this number here by 2. And then the carbon here, or excuse me, the C here is representing the number of carbons, okay? The H here is representing the number of hydrogens. The X is representing a number of halogens. And then the N over here is representing the number of nitrogens. I would imagine that other things that bond to this, we would look in their same family. So maybe if there was a phosphorus, maybe we would take a look in the nitrogen family. I'm not 100% sure about that, though. Probably shouldn't have said it on tape. Okay, let's try this one out right here. And I'll show you how I work the formula, and I'll show you how I can tell what it means, all right? So I'm going to start with this part of it here. So I have 2 times the number of carbons in this molecule, which is 3. And I'm going to add 2 to that. And then I'm going to subtract my hydrogens, which is 8. And I'll subtract my halogens, which is 0. And I'll add my nitrogens, which is 0. So when I do this, 2 times 3 plus 2, that's 8 minus 8 is 0. Divide that by 2 and you get 0, of course. Now what does that tell me now that I've figured this out? That tells me that this molecule is saturated. There are no pi bonds in it, and it doesn't make a ring. So this is just, propane, right? It's just CH3, CH2, CH3. So there are no pi bonds in it, and it's not a ring. Let's check out this next one, C4H8. We'll do the same thing, do the formula. So 2 times 4 carbons plus 2 minus 8 for the hydrogens, no halogens, no nitrogens. And so when we get done here, 2 times 4 is 8, plus 2 is 10, minus 8. That leaves me a remainder of 2, right? And divide that by 2, and I get 1. So it says 1 degree of unsaturation. Great. What does that tell me? That tells me it has either a pi bond or it has possibly a ring structure. So this could be this structure here. Let's take CH2, put a pi bond in there, a CH and a CH3, right? There we go. Whoops, I guess that wasn't right. There should be another CH2 here, yeah? And then another CH3. There we go. So it could be this structure here. It could be the structure that it is. I got the right number of hydrogens. I got 2, 3, 4, 5, 6, 7, 8 hydrogens, yep. Or it could be this structure, right? We could have another isomer of this if we move that double bond. So it could be CH3, could be CH, double bond in there, another CH, and another CH3. Now, does the degree of hydrogen deficiency tell me whether this molecule or this molecule? No, it doesn't. It only tells me that there's a pi bond in it. We would have to do other analyses. That's what those other analyses are for, and we can sit down and figure out how many or where how the carbons are arranged inside of this using other analysis techniques. But this would say, hey, at least there's a double bond in it, and then you could take this formula and write out all the possibilities for it, and then compare it to the other analysis information that you get to see which one it fits the best. There is actually one more possibility of this, and that is it could be a ring structure. So it could be bonded together like this. Cyclobutane would be its name. There we go. And this would also have 1 degree of unsaturation. Again, does the index of hydrogen deficiency tell me whether it's one of these two or this one? Nope, I would need more analysis to be able to figure that out. But it tells me that it's one of these 3 possibilities right here. That's how a scientist works. We take clues from each of the different ways and we put them together to see which molecule fits the best. Let's try this one over here. So I've got 2 times 2 carbons plus 2 minus 2, and then this one I have 2 chlorines in it, right? So minus 2, those are the halogens, and plus 0. So when I add this together, I got 2 times 2 is 4, plus 2 is 6, minus 2 is 4, minus 2 more is 2. So 2 divided by 2, I have 1 degree of hydrogen deficiency. So again, I know, hey, this has a pi bond in it. It could it be a ring? I would highly doubt it because chlorine tends to make just a single bond with carbon, but it could possibly make double bonds if we had expanded octets, but we don't want to go there, I don't think. So anyways, the carbon here, we have 2 carbons, and I'm assuming that there is a double bond between them. And that means it can bond to 2 other things. So one possibility, it could be like this, right? Maybe that's the structure of it. I don't know. Are there other isomers of this that it could be? Yes, there are. It could be this, right? So let's put our hydrogens on this side, all on one side, on one carbon, and put our chlorines on the other carbon over here. It could be either of these. This is what they call, I think this is called trans here, a trans configuration. Or no, this would be a cis configuration. And then it could be the trans configuration also. So of these 3 different structures like this, it doesn't tell me which one it is. I would have to figure that out with more analysis. All right, let's try this one with an oxygen in it now. So I have 2 times 1 carbon plus 2 minus my 2 hydrogens, and look at here, oxygen doesn't contribute to this formula at all, does it? So 2 times 1 is 2, plus 2 is 4, minus 2 is 2, so 2 divided by 2 is equal to 1. So this tells me that, hey, I've got a double bond in here. So I'm going to draw this one up here in this corner, huh? So I have a carbon. I know that I have a double bond. I have 2 hydrogens. I'm going to put them here. And yep, that double bond must be between the carbon and the oxygen, right? And there's our structure. See, so I have 1 degree of unsaturation here, and that is in that pi bond right there. It's not going to make a ring, right? And then finally down here, I have some methylamine. And so this one, let's run through our formula. I have 2 times 1 carbon plus 2 minus 5 for the hydrogens, minus 0 because there's no halogens, and plus 1 because there's a nitrogen, huh? So I've got 2 plus 2 is 4, minus 5 is minus 1, and then plus 1 would leave me at 0, huh? So 0 divided by 2 is 0. So this is telling me, hey, I don't have any pi bonds in this molecule. I can just draw this out from that information right there. Okay, let's try it with some more complicated molecules. So the first one on the top, first molecule is cocaine. It's the active ingredient, I guess, of cocaine here. And let's see. For this one, again, I have its structure here, but the goal is we're going to look at this formula and see how it matches up to this structure, huh? And in normal years, the IB would give you a test. They could either give you the structure and have you tell them how many degrees of unsaturation, or they can give you a formula and tell them how many degrees of unsaturation. But for us, we just want to see, how do chemists do this? They take this formula and then they match it up to the structure to see if it's giving them the right information or not. All right, let's work on it. So I've got 2 times 17 carbons plus 2 minus 21, no halogens, and a nitrogen, huh? So if I take this 34, 36, minus 21, that's going to leave me with 15, and then plus 1 makes it 16. So 16 divided by 2 is 8. We should be able to find 8 degrees of unsaturation in this. So what are we looking for? Pi bonds and rings, right? Pi bonds and rings. Let's find the pi bonds first. They're always easiest, it seems like. Here's 1 pi bond. There's another pi bond. Here's 3 pi bonds, right? So I've got 5 pi bonds in here so far. How about the rings? Well, this is an arene molecule, so an arene structure, so that's a ring. I can see this big thing right here. Do you see it? This is all put together to be a ring. So there's another one, another ring here. And then finally, there's a third ring right here. I don't know, it's kind of hard to see. So it has the nitrogen, and this nitrogen is bonded together with this carbon, and it's bonded together with that carbon. So all together, this makes like a ring here. Either way you want to kind of look at it, it's kind of like this ring is split in half or something, huh? So 1, 2, and 3 rings and 5 pi bonds, that's a total of 8. Let's check out cholesterol and do the same thing with that. I've got 2 times 27 carbons plus 2 minus 46, whoo, and then nothing else here. So 2 times 27 is 54. 54 plus 2 is 56. Minus 46, that's 10. Divide by 2. I'm looking for 5 degrees of unsaturation. Again, let's find the pi bond first. There it is. And then let's find the rings. 1, 2, 3, 4. 5 degrees of unsaturation. See how these match up? All right. So I have 2 for you. What I'd like you to do is press pause on this video, and then I would like you to go and work these out, just like we did on the previous slide, and then you can hit play, and I will run through them myself. All right. How did you do? Did you find all the degrees of unsaturation? I hope so. So I'm going to go 2 times 6 plus 2 minus 7 minus 0 plus 1, huh? Did you get that? 12, 14 minus 7 is 7 plus 1 is 8. Divided by 2 is equal to 4. And I can see 1, 2, 3 pi bonds in a ring, so that's 4 right there for aniline. And finally, down here, clonazepam, and clonazepam is a drug that they use for seizure control. So that's got a pretty crazy little structure over here, doesn't it? You imagine, telling somebody, here's the formula for this. Well, what is it, right? And so this just gives us clues for what this looks like. All right, here we go. 2 times 15 plus 2 minus 10, minus 1 for the chlorine, and plus 3 for the nitrogen. Did you catch all those? 32, 22, 21, 22, 23, 24. So I got 24 divided by 2, that's 12. 12 degrees of unsaturation. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9 pi bonds, and 1, 2, 3 rings. That equals 12. Okay, so I hope you figured out how to calculate how many degrees of unsaturation, either from the structure or from the chemical formula itself. And I hope you're able to see how we can relate the degrees of unsaturation to what's going on with the structure of the molecule. Until next time, have fun with your chemistry.